Of the many different methods of working with glass in the kiln, quite a few are based on fusing, or the heat bonding of disparate pieces of glass. In this lesson, we will focus on fusing layers of sheet glass and/or accessory glasses on a kiln shelf. In studying these fundamentals, you will begin to understand glass as a material and how you can work with it to realize ideas and designs. In this lesson, you will learn what glass fusing is, two basic types of fusing on a kiln shelf, how to control the volume of fused glass pieces, how to control line quality, how to control bubbles in fused glass pieces, and two basic firing schedules. Fusing is the process of bonding disparate pieces of compatible glasses with heat and gravity in a kiln. Glass is heated in a controlled manner to a process temperature and held until formed, then returned to room temperature again in a controlled manner. You can achieve a variety of effects when fusing by precisely controlling kiln temperatures. A full fuse occurs when the kiln has been fired hot enough and long enough to completely join pieces of glass together. The top surface of full fused glass is flat and glossy. The edges are softened and the corners rounded. In our kilns, glass becomes fully fused when it is fired to around 1480 degrees Fahrenheit and held for 10 minutes. The term tack fuse describes a wide range of results you can achieve by firing to temperatures below a full fuse. On the lower end of the tack fuse range, pieces of glass simply stick together and otherwise retain all or most of their individual characteristics. Low-temperature tack-fused pieces may have considerable relief. On the higher end of the range, closer to a full fuse, the pieces of glass show noticeable displacement and movement. They are also smoother than low-temperature tack-fused pieces. As heat within the glass increases, viscosity decreases, allowing gravity and/or surface tension to deform the glass. At full fuse temperatures, bullseye glass will assume a thickness of 6 millimeters. We call this the 6 millimeter rule. If you fire less than 6 millimeters of glass, surface tension will cause the material to pull in towards the 6 millimeter mark. If you fire more than 6 millimeters of glass, the stack will flow outward toward a thickness of 6 millimeters unless it is constrained by dams. All of these fired samples were originally the same size. These are pieces of our thin, 2 millimeter sheet glass. One has been fired, the other has not. During firing, the edges thickened and the center thinned as surface tension caused the glass to move toward a thickness of 6 millimeters. These are pieces of our standard 3 millimeter sheet glass. Again, one has been fired, the other has not. Comparing fired samples of our 3 millimeter and thin glasses, we see that the 6 millimeter rule applies again. Since the 3 millimeter glass is twice as thick, the edge deforms to a lesser extent. To create a full fused project in which the fired dimensions are the same as the unfired footprint, use a total thickness of 6 millimeters of sheet glass. Notice that the edges of the fired piece softened and the corners rounded, but the glass maintained its original footprint. These stacks consist of 4 layers of 3 millimeter glass. One is contained inside of high-temperature dams, the other is not. After firing to full fuse temperatures, the uncontained stack has flowed outward. If held at full fuse temperatures for long enough, such a stack would eventually flow until it reached a thickness of 6 millimeters. The stack that was contained within high-temperature dams, on the other hand, has stayed within its original footprint. The layers simply fused together, settling down to become slightly thinner than the unfired stack as air escaped from between the layers in the fusing process. Both methods of firing thicker pieces are valid. They simply yield very different results. Applying small pieces of cut sheet glass, frit, powder, or stringer to the top surface of a 6mm base allows you to extend the design possibilities. But if too much glass is added, or it is placed too close to the edge, it may flow out and distort the footprint of the finished piece, if not contained within dams. While this type of distortion can be a design feature, it may not be what you desire. To limit such distortion, keep material added to the top surface at least 3/4 of an inch from the perimeter, or dam the piece. The crisp lines and flat surface on this piece were achieved by composing with a method we call design down. To compose design down, build tightly fitting pieces directly on the kiln shelf and cover them with an uncut layer of sheet glass. The uncut top layer, or cap, will hold the seams in the bottom layer together during firing. The resulting piece will have crisp, clean lines and a very flat top surface. The softer lines and shapes of this piece were achieved by composing with a method we call design up. To compose design up, place the uncut layer on the shelf first, and then arrange the cut pieces on top. Lines between colors in the finished piece will be soft and irregular because some glass colors flow sooner and/or farther than others. Also, the unconstrained seams in the design may pull apart to reveal the base glass. When viewed at a distance, design up and design down tiles may seem quite similar, but seen up close, there is a world of difference. Proper design and firing methods will result in small, champagne bubbles between glass layers. Such bubbles are accepted as part of the handcrafted glass aesthetic. However, it is possible to unintentionally create other types of bubbles that may be large enough to rise and disturb the top surface. To maintain control over both bubbles and volume, always work in complete layers. To minimize air between layers, orient each piece with the smooth side facing up. If you can, design your work so that cut lines extend to the perimeter, allowing air a pathway for escape. Do not sandwich incomplete layers between complete layers or otherwise trap heavy textures between layers. Attention to these details will give you a much greater control over bubbles, yielding champagne bubbles instead of large distorting bubbles. While the design and layup of a piece are important for achieving desired results, the manner in which a piece is fired is equally important. The cycle described in this part of the lesson is for fully fusing a 10 by 10 inch plate, consisting of 2 complete layers of 3mm glass. For uniform heating and cooling of the glass, elevate the kiln shelf on 2-inch posts. Then program the kiln as follows. The first segment of the cycle encompasses both initial heat and the pre-rapid heat soak. Heat at a rate of 400 degrees Fahrenheit per hour to 1225 degrees and hold for 60 minutes. The second segment encompasses the rapid heat and process soak steps. Fire a faster rate of 600 degrees per hour to 1490 degrees with a 10-minute hold. The third segment in the cycle encompasses the rapid cool and the anneal soak. Cool the kiln as fast as possible to 900 degrees and hold it for 1 hour. Do not crash cool by opening the door. Allow the kiln to cool at its natural rate with the door closed. The fourth segment is the anneal cool. Program the kiln to cool at the rate of 100 degrees per hour to 700 degrees. A hold is not required as the schedule transitions to the final segment. The fifth and final segment is the cool to room temperature step. Program the kiln to cool as fast as possible to 70 degrees. Allow the kiln to cool at its own rate with the door closed. After firing, the piece will emerge with a smooth and glossy top surface, rounded edges and corners, and the disparate pieces of glass fully bonded together. To create surface texture and add design elements to either fully fused or unfired glass, place sheet or accessory glass components on the surface and fire to your desired tack fuse temperature. For uniform heating and cooling of the glass, elevate the kiln shelf on 2-inch posts. Then program the kiln as follows. The first segment of the cycle encompasses both initial heat and the process soak. Heat at a rate of 300 degrees Fahrenheit per hour to a target temperature between 1250 and 1450 degrees and hold for 10 minutes. The second segment encompasses the rapid cool and the anneal soak. Cool the kiln as fast as possible to 900 degrees and hold it for an hour and a half. Do not crash cool by opening the door. Allow the kiln to cool at its natural rate with the door closed. The third segment is the anneal cool. Program the kiln to cool at the rate of 75 degrees per hour to 700 degrees. A hold is not required as the schedule transitions to the final segment. The fourth and final segment is the cool to room temperature step. Program the kiln to cool as fast as possible to 70 degrees. Allow it to cool at its own rate with the door closed. After firing, the piece may have a wide range of qualities, depending on the top process temperature to which it was fired. On the lower end of the tack fuse range, pieces of glass simply stick together and retain all of their individual characteristics. This piece was fired to 1275 degrees and held for 10 minutes. Notice the considerable amount of texture still present. As temperatures increase, any glasses added to the top surface will soften and flatten more and more. At 1425 degrees, surface additions are much smoother and glossier, but there is still some relief on the surface. Now that you understand the 6mm rule, design up and design down, managing bubbles, and basic firing cycles, you are off to a good start in making successful fused projects using Bullseye glass.